We're still trying to find the three multi-combinations of x. We're trying to count them. And step one was to find the three multi-combinations with no limits on the numbers of the four types of items. Now we're going to subtract the numbers of illegal combinations. So, first, illegal means we cannot have more than one A, not allowed, illegal to have more than two B's, and illegal to have more than two G's. So let U be all the three multi-combinations. Let A be those with two or more A's. B has to be those with three or more B's. Remember, because there was only two B's in the original set X. And G would be those with three or more G's. Same thing. So the total was going to be U, the big number universe, minus the three illegal ways, plus the intersections pairwise, two of each, and then finally minus the triple intersection, A intersect B intersect G. This one turns out to be easy enough to do kind of by hand. We figured out 20 on step one. The rest of it you can do by looking at them. For instance, the number of them with two or more A's. I drew them all. You could have A and B, A and F, A and G, or three A's, A and A. There's four possibilities there. And with three or more B's or three or more G's, the only way to have three of something is to have them all be B's or all be G's. So there's only one of each of those. That explains the rest of those numbers. They're all going to be zero because there's no way, for instance, to have A intersect B. You can't have something that has two or more A's and three or more B's in it if there's only three total. Same for all the rest. It gets worse. You can't have B intersect G because there's no way to have both three or more B's and three or more G's. There's only three total items. So that turns out to be 14, which is the same number that we found by listing them all out on the previous page. So good, it works. We're going to do some more of these type of problems with harder to figure out parts, especially in chapter 6. We come back to this. This is a little bit of a preview of some more interesting problems then. But for now, we want to we've done multi-combinations, so now let's do some multi-permutations and see what that means. Multi-combinations are just subsets. Multi-permutation means that there should be some ordering to it. So this one I picked the second example set Y, and that's the one that has the letters in Mississippi. 1M, 4 I's, 4 S's, 2 P's. And the question is how many permutations of that? I would say complete permutations are what we're going to work with here, where we use up all of the letters. And if you use up all of the letters in a word and make a new word by scrambling them, people call it an anagram. So especially in the book, a lot of times they'll ask you questions about anagrams. Just means permute the letters. So here's the idea for that. This is another example of overcounting by a multiple and then dividing out in order to find the right answer. And the way we overcount by a multiplier is we pretend that the identical letters are really not identical. We pretend that they are distinct. You can do that by putting like a little subscript. So for instance, the I's, I'll put I1, I2, I3, and I4. I want to just leave it like that to make it visible, but I'm also going to do the same thing for the P's and the S's. There'll be P1, P2, and S1, S2, S3, S4. But just so you can see how the I's are working for now. Then you scramble them any way that you want to. And then you realize that what you end up with is a bunch of copies of the actual anagram for Mississippi, one for every rearrangement of I1, I2, I3, I4, because they're really actually identical. We pretended that they're distinct, but then once we we scramble them, we really don't want to count the different versions that look exactly the same except for the I1, I2, I3, and I4 being switched around. And so how many copies will we have? Well, for all the ways of rearranging I1, I2, I3, and I4, which is another permutation, 4 factorial ways to rearrange those, keeping everything else the same. So then we do that for P and for S as well. There's also 4 S's and 2 P's. And every time we do that for P and for S, it's independent of what happened to the I's, so we can multiply through by all of those to see how many copies we have. So the total answer will be 11 factorial. That's the number of permutations of all 11 letters in Mississippi. And then divide out by the product, 4 factorial times 4 factorial times 2 factorial. And I threw in times 1 factorial for the M. That's what those little arrows are showing. The I's, the S's, the P's, and the M's. So for every collection of this of actually identical elements, we divide out by that number, factorial, and those all go in the denominator times each other. And that came out to 34,650. Probably a good place to stop there. Yeah, next we have a bijection